The first one, presentation title is Lifetime Prediction for E-Mobility Driver Trains by Real-Time Simulation and Condition Monitoring. This presentation is by Professor Michael Otto. Professor Michael Otto is one manager at the Gear Research Center at the Technical University of Munich. He has done many research on gears and transmission systems, simulation and measurement with focus to load distribution and vibration. Okay. Please
Thank you.
roll the video.
Welcome to my presentation on lifetime prediction for e-mobility drivetrains by real-time simulation and condition monitoring. My name is Michael Otto from FCG at TU Munich in Germany. As an outline of my presentation, I like to give only these short 4 points. I'll start with an introduction, then I'll cover load spectrum calculation for vehicle individual application and pre-damage warning through condition monitoring, and finally come to a summary and give a short conclusion. The drivetrain is a critical subsystem in any vehicle, so failure has to be prevented. This means today safe design for any driver is applied. As a result, drivetrains are overdimensioned. That means are too heavy for most drivers and operating conditions. Especially in mobility, weight saving is mandatory, even more than in ICE vehicles today. A vehicle individual lifetime prediction, including pre-damage warning and service booking, would allow lighter drivetrain design. This means most drivers would still enjoy no failure operation during vehicle lifetime. Few challenging drivers would need to get some additional service during regular service intervals. And only the most challenging drivers and operating conditions would require extra service. That means any road failure of drivetrain would still be prevented, and safe and reliable operation would be guaranteed. The methodology is presented by example of gear life calculation, since gears are central components of drivetrains. Load spectrum calculation is widely known and applied. For gear meshes, according to the international standard 6336 and the parts of the standard, and various specialized software suites are available that allow detailed calculation, for example, FEA Workbench, Romex Designer, SMT Master, GISsoft, and a lot more. But it is not feasible to run calculation models for every vehicle individually and continuously during operation due to calculation time and effort. Several condition monitoring approaches, on the other hand, are documented in the literature. But also here some drawback exists. Most of these approaches rely on detecting changes in behavior, indicating a damaged element. No feedback on type of damage and possibility of ongoing operation is given. The proposed methodology in the following is presented on some calculational values which are based on an example of a gear stage from high-speed mobility gearbox, which was designed and tested for the project Speed 2E for an input speed of up to 30,000 RPM. On the right side, you see a transverse sketch of the high-speed gear stage that is taken as a basis. Starting with the flank load capacity, according to ISO 6336, we like to focus on these three central equations. We need to determine the relevant contact stress, which is possible after the top two equations given here. So we have contact stress sigma H0 for gear 1 or 2, which is determined by multiplying factors ZH, ZE, Z epsilon, Z beta, that generally transport information on geometry and material of the gears. And then the square root term is multiplied on it, which includes the term Ft, which is the transverse force in the gear mesh, and some additional terms based on gear geometry. The calculation then continues to yield the relevant contact stress sigma H for gear 1 and 2. Again, some factor on geometry, it's called ZB or D, is multiplied on this result from the above equation, sigma h0, and then is multiplied by a square root term which transports overload factors. So this is the factor Ka for external overloads in the gearbox, Kv for internal overloads depending on gear dynamics, and factors Kh beta and Kh alpha which transport contact overloads due to uneven load distribution in the contact. We need to determine an allowable contact stress as well, which is done by the third equation, giving allowable contact stress sigma hp, which is then determined by value sigma h lim, which is derived from the curve in the standard, and again several factors z and t, which determines load cycles, zl, zv, zr, which are determining some lubrication and running conditions, zw, which is something covering different materials of the gears, and zx, which covers the size influence of gears. I don't want to explain all these factors in detail because these can be looked up in the standard very well. But I like to come to the use of these equations, and at first we need to focus on the values that may be dependent on operating conditions. So we find here transverse contact force, which definitely is dependent on the operating moment. We find these overload factors, which as well are dependent on the operating torque moment and on the operating speed in the case of Kv. And also on the side of the allowable contact stress, we need some input values. We need an allowable stress, which can be derived from the SN curve from the standard. And we need, in this case here, some factor dependent on operating speed, which we will simplify, so this can be looked up in the paper. Now these equations concerning spectrum calculations are used to calculate the full load spectrum, and then we may get a graphic like given on the right side as an example now. This graphics, on the vertical axis you find the contact stress, and on the horizontal axis you find the number of load cycles. Now in this graphic there are these black lines which characterize the SN curve for 1% failure probability here. On the left side you find this dashed line which goes up to the left, which is an extension of our load capacity we use here. It's commented in the paper. Special care has to be taken if this extension is used. And the load spectrum itself is characterized by this blue line, which is given throughout the graphic. And this is the actual load spectrum. You will see an additional red line as well, indicated as allowable load spectrum. But let's focus on the blue line before. This is a lot of loads and the accordingly applied load cycles. And looking at one example, we see this light green small arrow, which indicates on a certain contact stress level the number of load cycles that are determined at a given stress in this load spectrum. And on the same stress level, we can now determine how many load cycles are allowed until failure by just looking to the SN curve. And by dividing both values, the load spectrum calculation assumes that this gives a portion of lifetime that is used at this stress level in the load spectrum. Now, the full load spectrum calculation demands that we calculate for every load such portion of lifetime, sum up these damaged portions, and then to determine some distance to full usage of the lifetime, an iterative calculation is demanded for an allowable load spectrum. And this is how this red curve, which is in this graphics nearly identical to the blue curve, is determined. The load spectrum is scaled, full calculation is run again, and then iteratively the load spectrum is scaled to a life usage of 100%. And then we have some information on how critical our load spectrum is. So quite a complex procedure. Come to the next slide where we see, well, in effect, nearly the same picture, but different focus. this is the calculation of tooth root capacity, which we need to run as well. It's working after the same scheme, so I don't want to explain this in detail. It's in general similar to flank load capacity that we just focused on the slide before. Now we can, of course, write up the whole load spectrum in a numerical way, which is given in this table here. So we will use this as a basis for approach to come to a fast calculation. So if we start at some load spectrum that is ordered in different torque moments, like given in this second column here, and determination of load cycles, then we can determine damaged portions of flank and root, like given in the further columns to the right. Now the values here are derived from a given load spectrum, which was used to design this hyper-high-speed drivetrain. But of course, we could just predetermine certain load levels that we want to use, and then sort our operating condition load levels in these pre-calculated load levels. And this is what we'll do. So we can, for every load given, conduct a detailed design calculation of stresses, and do this, of course, for many loads at design time, and arrive at some tabulated results for every load level. We have here the overload factors, KV, KH beta, KF beta, KH alpha, KF alpha, and the stress levels for tooth flank and tooth root. And what we can do on this basis now is, during operation, we can just, for every current operating load, look up the right line, which values apply, and then continuously calculate the portion of used lifetime very fast, because we only need to compare number of load cycles to number of allowed load cycles, and sum up the damaged portions. And while continuously summing up damaged portions, we see that our used lifetime increases, and we just need to check if and when our damage sum surpasses some predefined threshold. At this point, we come to pre-damage warning through condition monitoring. The load spectrum calculation has certain imprecisions, but a precise damage prediction and warning is necessary. So we like to employ a condition monitoring system with damage recognition and prediction of runout capability. The graphic to the right, the result of such condition monitoring system applied to a gear test is shown. On the vertical axis, the normalized signal power is shown, which was an indication for tooth root breakage in this evaluation. And on the horizontal axis, the normalized time of the test is shown. And now the focus is given only on 0.994 until 1.0 of the time span used in this test, so at the very last phase of the test. And we see that until 0.996, nothing is shown. At this point, the blue line goes up. And this blue line is attributed, in this case, to tooth number 8, and indicate that the signal for starting tooth root breakage is severely going up. So with this algorithm and this result, it would be very clear at this point of time that tooth root breakage is developing, and some measures would have to be taken to prevent a full breakdown of this gear mesh. Now, an alert level could be generated by relying on calculated damage portion spectrum calculation and including the result of monitoring, for example, after surpassing certain thresholds of the calculated damage level. We could use this calculated damage sum and condition monitoring indication to determine a service scheduling. So, knowing the damage type that is developing, could separate it, for example, and evaluate a developing pitting damage, then normal schedule of service would be sufficient. But if we indicate, for example, to the root damage, the risk of a total drivetrain breakdown, we maybe need to rely on a reduced power operation and immediate service scheduling. So I like to come to summary and conclusion. A lighter drivetrain design is possible by timely pre-damage warning for challenging drivers and operations. The proposed approach for fast vehicle individual calculation would be to conduct a detailed design calculation of stresses for many loads at design time by using specialized software. Then tabulate the results. And during operation, use a continuously sum up of damage portions and include results by condition monitoring before reaching critical damage portion. And on this basis, it should be possible to determine the type of damage that is detected, decide on run-on capability, and then indicate to the driver the drivetrain status and schedule an immediate service if a critical damage with limited run-on capability is detected. Thank you for listening to my presentation, and please feel free to contact me for any questions.
Okay, if any question from on-site or from online?
Yeah. Okay,
Yes.
Professor Otto, my name is Nong Zhang from Hebei University of Technology. Very interesting presentation. I guess you put the emphasis on the e-mobility. So you assume the powertrain will be driven by motors, and your gear sets will be different from the conventional, say, gearbox or transmissions. Am I right on that?
We need some kind of special design for high speed.
Yeah.
But as I showed with this transverse section of our test gears, they're not totally different, but of course specialized for this application.
Okay. So I guess the load pattern compared to the conventional vehicle probably will be different because your speed. Then your driving motor speed could be high, vehicle speed will be the same. So the difference is gear ratio. Your gear ratio is say probably larger than usual. Then
Exactly.
yeah. So that would be a problem. And when you're talking about the monitoring, what is the main sort of monitoring the information will tell you the gears is not in good condition or in good condition. So what sort of data you will get for monitoring the situation, the condition?
In our test, we used accelerometers plus an angular measurement system. Of course, if we go to very high speed, angular measurement does not have detailed enough information, so then we rely on accelerometers. And we have a special evaluation algorithm that gives this picture in one of the last slides to determine what tooth and what type of damage we need to assume. But it's in general, it's a signal from accelerometers placed on the gearbox.
When it's acceleration transducers measures the linear motion, but here rotational motion is of your interest, right? So how do you actually measure the angular acceleration?
Yeah, exactly. As I said, we used both systems, accelerometers on top, which measures linear acceleration at bearing position. This is due to the fluctuation of the radial gear force, okay, which always is resulting from torque moment fluctuation. And we also used angular measurement system. So this was an optical system with a lasered on barcode, but this is only possible in test rig operation. Yeah. So we could not use it in the real gearbox because it needs to be out of the oil space. So we need some space, and we used this angular measurement only on test rig to calibrate the algorithm.
Good. So that's the point I want to come to there. You probably will do the test at the laboratory condition to get the angular measurement, then correlate you to your linear translation signal to find some sort of a common feature or commonality, right? So
yes, exactly.
Thank you.
And
I'm all right. Yeah.
Just one comment. Very good question. Thank you for discussion, and especially to determine which type of damage is present in the gears. We need exactly this pre-calculation to formulate a good algorithm.
Yes.
Thank you. I think I'm over time, but
Thanks for discussion.
It's a good talk, good sort of presentation. Yeah, thank you.
Okay, thank you, Professor Otto. Any more questions?
Thank you very much.
Any more questions? Okay, thank you.
Thank you.